All right. Oh. All right. Okay, so it's 4:06, so I'll get started. Good thing I caught all my swearing on the recording. But yeah, this is COMP2804 Discrete Structures 2, and I'm Daryl Hill, the instructor. Where are we? On the 16th. So assignment 3 deadlines coming up. I will briefly talk about one of the questions. I'm getting some questions. I think you can, for the most part, intuitively figure it out, but I will sort of go over and you know, show how it relates to what we took in class. I'm just not sure. I don't know. I've been getting some questions about it, so I'll just address it. So yeah, assignment 3 is due this weekend. Assignment 4, I don't know if you guys are eager, I'll probably release it. I could release it tomorrow probably. And then test 2 is next week. So yeah, we will take up some test 2 questions or type questions on the 21st in preparation. But otherwise, any questions before we get started? Okay, so I wanted to talk about releasing the answers before the test. Yeah, for sure. The answers I'll release. So technically Monday morning, whenever I get in after 8 o'clock, I will release the answers. So I did want to address this one. It's perhaps more complicated than, I don't know. It's pretty complicated for an early question, but question 3D. So what happens is that I am asking for the probability that I have 30 home runs, 10 are hit into the upper deck, 10 are hit into the lower deck, which means that 10 are hit out of the park as well, and that no one in the upper deck or lower deck catches more than one ball. Okay, so this relates back to the lecture on conditional probability where we talked about, well, I guess the example that would be most like this was I flip a red coin, and if it comes up heads, I flip a blue coin and I return whatever the result of that is. Or if the red coin comes up tails, then I roll a die instead. So now I can have, this is not a uniform probability space, but what happens is if I flip that red coin and it comes up tails, then I look at that probability space, that event, each outcome in that event has uniform probability, right? So that's the idea behind this, is that, I'm looking at the first event is that 30 home runs are hit. And then out of that, the sample space is that 30 home runs are hit, and if they're hit into one of the stands, then somebody catches them. And then out of that sample space, I want the event that 10 are hit into the upper deck and 10 are hit into the lower deck. And then once it says here, 100 people in the upper deck, and every time a home run is hit there, the ball is caught by one person uniformly at random. So if I look at all of the outcomes where, let's just keep it simple for now, we'll just talk about the upper deck. So let's look at all of the outcomes where 10 balls are hit into the upper deck. And then I look at all of the distributions of who those balls were hit to, and that's a uniform probability space, just that event, right? So the entire probability space is not uniform, but the event that 10 balls were hit there, then if I look at who those balls were hit to, those are all uniform, right? So the little trick that we did there for the, so let's say if A is 10 balls are hit into the upper deck, let's call that B actually. And A is, no one catches greater than one ball. So this event B, if I look at that probability space, everything in that event is uniform probability, which means that if I asked for the probability of A given B, then I can compute that using this uniform probability, right? So I know the size of, because these are all uniform probability, I can say, if I ignore the rest of the question and just say, well, what is the probability that no one catches more than one ball, given that 10 balls were hit into the upper deck? Well, you know how to compute that. It's a uniform probability space, so you can use, well, 10 balls, all the ways that people can catch 10 balls, that's your sort of limited sample space. And then all of the ways that no one person catches more than one ball, that's the size of your event. Yeah. Again, be consistent, but as long as your sample space and your event space, if you're doing it in order, then they are both in order. If you're not doing in order, then they're both not in order. So yeah, that is sort of the trick to this. And as a hint, right? So this is no one catches more than one ball, given that 10 balls are hit into the upper deck. Well, then I just compute, I just say that my sample space is now 10 balls are hit into the upper deck. What's the probability that nobody catches more than one, right? So I can figure out that probability without necessarily using the other formula, right? Because this event is uniform probability, I can just compute it directly. Okay, so hopefully that makes sense. The other thing, what we're actually trying to find in this question is the probability of A and B. Right, so that's what we want. The probability that 10 balls are hit into the upper deck and no one catches more than one. But I can, this is, if I look at my formula for conditional probability, it looks like this. So if I want to isolate this part, I can multiply both sides times the probability of B. So now this is what I want to find, the probability that I hit 10 balls into the upper deck and no one catches more than one. And I can compute this probability directly because that event is a uniform probability space. So it's just counting, right? I just ignore the numbers of ways that I can hit 10 balls into the upper deck, and I just assume 10 balls are hit into the upper deck. And then this is the probability that 10 balls are hit into the upper deck. Okay, so we did cover this. I don't know if it was emphasized enough. I felt like it deserved a review. So any questions? Yeah.
Also 10 balls.
Yes. So that's the extra wrinkle that you guys will have to figure out. Yeah. So yeah, this is what I'm talking. I just did a simplified version of the problem where we just talked about the upper deck. But yes, you also have to account for the lower deck, but the same things apply, right? So once I assume 10 balls are hit into the lower deck, I can treat that as a uniform probability space. So then I can calculate my conditional probability just using counting instead of the traditional expression. Hopefully that makes sense. It is sort of a question where you can kind of be guided by your intuition as well, right? So in this case, if you feel like the right answer is such and such, you might be right. All right. All right, so today we are going to talk about random variables. So I really like this part of the course. It gets more and more interesting, or at least the problems that we can solve get more and more interesting. It's still a lot of math, of course. But yeah, let's talk about random variables. It's possible that we will also start expected value today. This is, I think, a short lecture, but we'll see. Okay, so what do we know so far? Well, we know how to, we know what a sample space is, and we know what an outcome of our sample space is. We perform some experiment, and an outcome is what happens. An event is some subset of the sample space, so it's just a collection of outcomes. And then we have a probability function on those outcomes. So for, every outcome in my sample space, there's a certain probability associated with it. And if I sum up all of those probabilities, they all sum to 1. Okay, so now we're going to add another function to this setup, a random variable. So what is a random variable? Well, it's not random and it's not a variable. So that's very aptly named. It is basically just a function. It's a function that maps, I take an outcome from my sample space and I map it to a value, right? And so why would we want to do this? Well, there's lots of reasons. We will see some examples, then we'll explore that a little further. But essentially, we've already seen random variables, right? So when we talked about rolling two dice and taking the sum, what we did implicitly is we defined a random variable that mapped an outcome, which is, right? So if I roll 2 dice, this is what my sample space looks like. My outcome is a pair of numbers, I, J, where I is the value of the first roll and J is the value of the second roll. And then we implicitly sort of mapped that to the sum of those two rolls, right? So if I look at this outcome, we implicitly mapped it to the value which was adding I plus J together. So yes, so our random variable X is a function that maps the sample space to the real numbers, okay? Any real numbers we want. We choose real numbers that make sense in the context that give us some information that we want. In this case, the information that we want is the sum of these two dice rolls. Okay, so Xij equals I plus J, so it's simply a function. So for instance, if I roll 2 on the first die, 2 on the second die, then this function X, this random variable X, is equal to 4. Okay. So yes, random variable is a function that takes an element of the sample space as an argument, maps it to a value. Any value we want. Most of them are kind of sensible, but we could make completely nonsense values if we want. So we have, this is our random variable X, which is the sum of the 2 dice. And we can write it out like this, but typically we just describe it in English. We'll say that the random variable X is equal to the sum of 2 dice, let's say, not rolls. And we often, although the proper way to write a function is to supply the arguments, but we'll often omit the arguments. We'll just say X, and then that will take on a certain value depending on the outcome. Or we can, well, we'll see a bunch of different ways to do it. Okay, so that's the dice roll one is pretty straightforward. We have a function that maps the sum. But let's take a look at another experiment. We flip a fair coin 3 times. Okay, so the sample space has 8 elements, heads, 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 or heads, heads, tails, and so on and so forth. All of the possibilities when I flip 3 coins. And then I can define a random variable based on whatever I want. So let's say that in this case, X is the number of times this coin comes up heads in my 3 flips. Okay, so we can define this explicitly. I can, supply the outcome as an argument and then map that to a value, right? So I can say, well, if the outcome is heads, 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 then the value is 3. And I can say, well, heads, heads, tails, the value is 2 because I have 2 heads. So this is, one way to define it, and it's not wrong. Yeah, so we can define a function this way. And then let's take a second random variable y on the same sample space. So in this case, y is equal to 1 if all 3 flips are equal and 0 otherwise. So if we map that out explicitly, well, if we get heads, 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 y is equal to 1. If we get heads, heads, tails, it's equal to 0, and so on and so forth, right? And if it's tails, 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 it's equal to 1, everything else equal to 0. Okay, so it's much easier just to describe them in English. We don't typically do this. Again, it's not wrong. But yeah, we would basically just simply say X is the number of heads in 3 flips, and Y we can define like this. There's only 2 values for Y, so all 3 flips are equal. It's equal to 1 and 0 otherwise. Okay. All right, questions so far? Yeah. I don't know. Just to confuse you, I guess. But yeah, it's just a function. Yeah. Yep. That's a good question. I should look that up. But yeah.
X number of heads. Why is there X is like tails and 0?
Oh, did I mess up somewhere? Yeah. All right. That's typo. Yeah. There's yes. Thank you. I'll try to remember to fix that. But other questions? Okay. All right. So now we have our event space, or sorry, our sample space. We have our probability function, and we have our random variables. Now we can define events based on these random variables, right? So an event it's still the same definition it's always been. It's a subset of the sample space. We typically describe it in English, but now we can describe it using these random variables and their values, right? So every value of a random variable also corresponds to a subset of the sample space. So for example, I can say the event X equals 0, right? So X is the number of flips, or sorry, number of heads in 3 flips. So the event X equals 0 is the event that there are no heads in 3 flips, right? So it's just tails, 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 right? So all of these are equivalent statements. They're all events, and they're all equivalent. And I could say the event that X is equal to 1, well, there was 1 head in 3 coin flips. So I take a look at my sample space and I look at each outcome that only has 1 head. And that is head, tails, 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 head, tails, or tails, tails, heads. So this event X equal to 1 corresponds to this subset of the sample space. And, I could also describe it in English. There's 1 head in 3 coin flips. I could do X2, 3, that's fine. X equal to 4. I could, I could define that as an event. So I could say there were 4 heads in 3 coin flips. Of course, this event is empty. There's no outcomes that have 4 heads in 3 coin flips. So yeah, that would be equal to the empty set, which is also an event. For the random variable y, I could say the event y equal to 1 is heads, 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 and tails, 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 right? So this is all 3 flips are equal. And y equals 2 is, of course, meaningless, right? So that's the empty set. It's, well, according to our definition here, it's undefined. So I have not mapped it to any outcome of the sample space. So this event is also the empty set. And yeah, I can also say y equal to 0. and include everything else here, but I think you guys get the idea. Okay, so yeah. All right, so here's some events. Now, actually, here's basically all of the non-empty events associated with X and Y. So in general, for my random variable X, an event X is equal to K is just all of the outcomes in my sample space such that this random variable is equal to K. All right, so this is, a lot of this seems redundant. I'm going to repeat myself here a little bit as well, but this does become actually useful when we get to expected value. So I have a sample space. I have a, a set of real numbers. And so my function X, well, I have a subset of my sample space that maps to a value K, right? This is now my event X is equal to K. All right, so now the probability that X is equal to K, well, that's an event. We know how to compute the probability of an event. We simply sum up all of the individual probabilities in that event, right? So if I looked at this event, X equal to K represented here, I take the probability of this outcome plus the probability of this outcome plus the probability of this outcome. Okay, and that's my probability that X is equal to K, which is, again, just an event, could be described in English as well, but yeah, this does become useful. So for instance, the probability that X is equal to 0, that corresponds to the event that I have 3 tails and 3 coin flips. That has probability 1/8, which, I could, yeah. So the size of the sample space is 8. And then the size of this event, tails, 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 is 1. Okay, so yeah, we determine the probability of these events the same as we have for events in the past. The probability that X is equal to 1, well, now the size of my event space is 3. Since this is a uniform probability space, it's 3 over the size of the sample space, or 3/8. X equal to 2, also equal to 3/8. X equal to 3, that's equal to 1/8. And so yeah, we have probabilities for every event, every non-empty event on a random variable X, right? Every other sort of event defined on X is empty. It's a probability of 0. So if we sum up all of these probabilities of non-empty events, they sum up to 1, right? So my random variable all the values should span the entire sample space, okay? Yeah. If I look at the event, the random variable Y, and I look at the events associated with Y equal to 1 is either all tails or all heads. That's size 2 over the size of the sample space, which is 8. So that's 1/4. Y equals 0 is everything else, right? This is given by the other Y's. So there are 6 other elements that are not in Y equal to 1. So now that's 6/8 or 3/4. Okay, and again, if we add these up, we get 1. Right, so the values of Y span every possibility in the sample space, and there are only 2 possibilities. This is basically one is the complement of the other, and that's sort of communicated here as well, right? Where I say this defines one event, and then this defines every other event. So one is the complement of the other. Okay, so yeah, when this is the case, we can use the complement rule. We only have 2 values, non-empty values for our random variable. All right, questions so far? All right. Okay, so we're not limited to events where they're just equal. We can do events where they're it's an inequality. So I can take the event x is greater than or equal to 2, and then that defines this subset of the sample space. I have 3 heads here, 2 heads here, 2 heads here, 2 heads here. So this falls under that. And then the probability of that is, of course, just the size of the event over the size of the sample space, 4/8 or 1/2. You could also express this event as, the union of x equal to 2 or x equal to 3. In this case, these are disjoint, so we can use the sum rule, right? So if we have 3 heads, we definitely don't have just exactly 2 heads. We either have exactly 2 or exactly 3. So if I, sum up these probabilities, I get 3/8 plus 1/8 is equal to 1/2. Okay, so I mean, nothing particularly new here. It's the same old definition of events. We just give them a different name based on our random variables. All right. Good, everybody? No questions so far? Okay, so we're going to take our 2 random variables, and now these define a bunch of events. And now we can talk about, events A and B. If they're independent, well, then the probability of A and B is equal to the probability of A times the probability of B, right? That's the test of independence. That's the definition. This should probably be intersection. Okay, so if I have 2 events and I verify this equation, then they're independent events. And since our random variables define events, we can talk about 2 random variables being independent. So what that means is that, well, in English, if I know the value of x, then I know some event has happened. And then I can ask myself, does that have any influence on the probability that y has any particular value? And likewise, if I know the value of y, then I also know an event has happened. Now, does that give me any information on the probability that x has any particular value? Or the probability that x is equal to k, given that y is equal to L, is equal to the probability that x is equal to k, right? So if I know something about y, that does not change any of the probabilities of the values of x, and that's for all k and L associated with these random variables. Okay, so So 2 random variables x and y formally are independent if for all k and all L, the events x equal to k and y equal to L are independent. So this is like, remember how boring it was to do these equations for independence? Now with random variables, you get to do many times that many equations. So it's a lot of extra tedious work, but again, these do have importance. So if I have events x equal to k and y equal to L, then the probability of both of these events happening is equal to the probability of x equal to k times the probability of y equal to L. And I have to look at this equation for all possible values of k and L, right? All possible non-empty values. Right, so this is kind of a pain because there can possibly be many values for k and L. So it's often easier to prove that they're not independent, because to prove they're not independent, I just need one value for each of them. So logically, I want to show if they're independent, then this is true. And I'm going to take the negation of this, right? If we remember our quantifiers and negation, if I negate these quantifiers, these for all k and for all L, turn into there exists a k and there exists an L. And then I basically negate this part. So that means this statement turns into there exists a k, there exists an L, such that the events x equal to k and y equal to L are not independent. So that's all I need, is to find one value for x and one value for y. those two events are not independent. And then I'm done. You don't have to verify any of the other possible equations. Okay, questions? All right. So this is what we want. We just want to maybe use our intuition or what we know of independence. So we want to find two values K and L such that these two expressions, or the left-hand side, is not equal to the right-hand side here. Okay, so let's take a look at our events X and Y, or our random variables X and Y, and see if they're independent. Any guesses? Or not even guesses, but even evidence, or yeah. So, okay, well, this is still kind of new. So they are independent. Yeah. If we wanted to prove that they're independent, we have to look at all non-empty values, right? So for X, it's 0, 1, 2, and 3, and for Y, it's 0 and 1. So all combinations, 4 times 2 gives me 8 different combinations. So 8 different equations I would have to verify to show that X and Y are independent, right? So I start with Y equal to 0, and then for Y, you can think of it as a double for loop. For Y equal to 0, I look at all values of X. Okay, so I have to verify those 4 equations, and then I look at Y equal to 1. And again, I go through all values of X. So if we want to show they're independent, we have to show all of these equations, but we want to take a shortcut. So we want to find 2 events that are not independent. And so what I really want to say is that, well, what if Y is equal to 0, right? Or actually probably Y is equal to 1. So I know Y equal to 1 is the event heads, 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 and tails, tails, tails. Now, does that tell me something about the value of X? So if I know that Y is equal to 1, am I still in the completely in the dark about the value of X? Or do I now know something? Yeah. Right. X can't be 1 or 2. So X is the number of heads. So if Y is equal to 1, then X can only be 3 or 0. So our intuition is telling us, I have 2 values that provably influence each other. Right, so if Y is equal to 1, then what are the possible values for X? We can have X equal to 3 or X equal to 0. So now we have to find 2 events that are not independent. So if we look at X equal to 2 and Y, so if X is equal to 2, then Y must be equal to 0, right? Because for X equal to 2, I do not have 3 of a kind anywhere in here. So that's another example of 2 events that influence each other. Sorry, influence each other. All right, so we need to find one set of values. And the easiest thing to do is to find a value for X and a value for Y such that the probability of both of them happening is 0. That's the easiest way to prove that these 2 events or these 2 random variables are not independent. Okay, so probability that we look at K equal to 2 and L equal to 1. So the probability that X is equal to 2 and Y is equal to 1 is 0, right? That's an empty set. So it has a probability of 0. But we know that the probability that X is equal to 2 is not 0. And we know that the probability that Y is equal to 1 is not 0. So whatever values they are, they're not going to be equal to 0. They might be very small, but they will never be 0 unless one of them is 0. Okay, so X and Y are not independent. Yeah. All right, questions? Okay. Yes, not equal to 0. All right, so let's introduce another random variable. Z is equal to 1 if the first flip is heads and 0 otherwise. So now we can start thinking about, well, let's first look at, we know X and Y are not independent, but what about Y and Z? So, we either verify, well, in this case, we don't have 8 equations to verify. Y has 2 values and Z has 2 values. So Y has 2 events, Z has 2 events. We have to look at all combinations. So in this case, there's going to be 4 possibilities. Right, so it's not quite as bad as the other one. And maybe there's a lot of symmetry that we can take advantage of. All right, so, but instinctively, is there any 2 values here where you can say, well, if I know Y is equal to 1, then I must know something about Z. Or if I know Z is equal to 1, then I must know something about Y. Or does it seem like it doesn't matter if I know something? Right, less clear here, but we can start by, we can start verifying our equations. So the probability that Y is equal to 1 and Z is equal to 1 is, well, Z is the first flip is heads, and Y is equal to 1 is all 3 flips are equal. So that consists of a single outcome, right? So then the probability of this is the size of that over the size of that sample space, which is 1/8. Now the probability that Y is equal to 1, all 3 flips are equal. Yeah, there we go. So that's 2 outcomes. So the probability that Y is equal to 1 is 2/8 or 1/4. And the probability that Z is equal to 1, well, Z is all of the outcomes where the first flip is heads, which is half of them. So the probability that Z is equal to 1 is 1/2. Okay, so now we know all the probabilities. We plug them in. This is, this is 1/8. This is 1/4, and this is 1/2. So 1/8 equals 1/4 times 1/2, which is true. So these 2 events, Y equal to 1 and Z equal to 1, are independent. Okay, so we have 3 more equations that we should try and verify to show that they're independent. All right, questions? Okay. All right, so the next one, Y equal to 1 and Z equal to 0. Well, Y equal to 1, all 3 flips are equal. Z equal to 0 means the first flip is tails. Okay, so then both of these events together is just tails, tails, tails. So the probability of that is 1 over the size of the sample space, which is 8. So it's 1/8. The probability that Y equals 1, we already determined is 1/4. We did that on the previous slides. Z equal to 0. Little typo. Z equal to 0 means the flips all start with tails. So that is half of them. So yeah, the probability that Z is equal to 0 is 1/2. Now I know all my probabilities, and I get 1/8 for here is equal to 1/4 times 1/2. 1/8 is equal to 1/8. So these 2 events are independent. Okay, so let's look at the next set. Again, is going to be kind of symmetric, or not symmetric, but definitely easy. So Y equals 0 is not all 3 flips are equal. Z equal to 0 is the first flip is, Z equal to 1 is the first flip is heads. So it starts with heads, and I must have 1 tails in the latter 2 flips. So we either have heads, heads, tails, or heads, tails, heads, or heads, tails, tails. At least 1 tail. Okay, so that has size 3. So the probability of this event is 3/8. Event Y equals 0, well, we can use the complement rule here. So this gives me 1 minus 1/4, which is 3/4. Z equal to 1, we could have used the complement rule, but Z is, the probability of both of those is 1/2. So That's equal to 1/2. 3/4 times 1/2 is equal to 1/8, or sorry, 3/8. So that means these events y equal to 0 and z equal to 1 are independent. Okay, so we have 3 equations down and 1 to go. Y equal to 0 and z equal to 0. So none of them, they're not all equal, and they start with tails. There's 3 outcomes in that event. That's probability 3/8. The event y equal to 0, so this should be the probability that y is equal to 0. I use the complement rule. We already did that. We got 3/4. And event z equal to 0, well, both of those events are equal to 1/2 probability. So again, we have 3/8 is equal to 3/8. All right. So y and z are independent random variables. Okay, because we verified all 4 equations. So that means I tell you y is equal to 1. What's the value of z? And you say, well, I really don't know. The probability is still the same as it was when I didn't know anything about y. All right. Yes. Okay, yeah. Questions on that? Yeah. No, you have to go through every scenario, but usually, so if I ask you a question on these, so usually we use independence sometimes. That's going to be the primary thing. If I ask you, I mostly ask you to prove that they're not independent. It's easier to find. You use your intuition or, try out different values. Yeah, this is tedious, I get it, but again, it's the property of independence. So we're giving you the foundation. So what are independent random variables? So and then you can use it later on. Other questions? Okay. Are x and z independent? So yeah. Are they? Or what are 2 values that contradict each other? Are there values for x and z that both can't be true at the same time? Yeah. That's true. Yeah. So if we have x equal to 3, then we cannot have z must, we have, sorry, this implies that z is equal to 1, and we cannot have z equal to 0. So x equal to 3 and z equal to 0, this is the empty set, right? So then it has a probability of 0. So if all 3 are heads, then the first flip cannot be tails. Yeah, so these are not independent. So, I mean, I suppose I would accept this. Well, no, I can't really. You still have to verify at least one equation is not true, because if all of them have probability 0, then you have a problem. So yeah. Probability of this is the probability of the empty set, which is 0, and these are not empty. So yeah, x equal to 0 has probability 1/8, z equal to 1 is probability 1/2. These are not equal. So yeah. This is finding 2 events that are the intersection is empty is great. You're probably there, but you should still verify this equation. Okay, other possible candidates, z equal to 0, then x cannot equal 3. Yeah. So we only need to find one example. There's lots of such dependencies in this example, but all right. So distribution functions, how are we doing? These don't come up a lot, but when they do, I just want you to have a definition. So all it is, well, if I have a random variable, and I have a, a probability associated with the event of that this random variable is equal to a value, then I map all of these events to probabilities. Right, so if we, for instance, roll 2 dice and our random variable X is the sum of the red die and the blue die, and I look at all of the events that span the entire sample space, then I have a probability function. I look at all of the probabilities of each of those. That's a distribution, a probability distribution. Okay, so yeah, it's not, again, it doesn't come up a lot, but when it does, I just want you to be aware. All it is the probabilities of each of these events mapped out. All right, and of course, they should all sum to 1. Right, all the probabilities. Okay. All right, so yeah, we might get into expected value a little bit today, but yeah. All right, we'll do one more example with a lot of, it has a lot of, this is sort of relevant. So it is a bit tedious, but there's a lot of symmetry here that we can take advantage of. So it'll go kind of quickly. And then I think we'll move into expected value. This is sort of not the longest chapter in this subject. So if I have a set S, that's my sample space, and I pick one of those outcomes uniformly at random, right? So each of them has an equal probability of being selected. And then I define 3 random variables on this sample space. So independence has one more, of course, property to it. So we could show that we want to show, prove or disprove that they are mutually independent. So I have 3 random variables. Before I just compared 2, and we showed that they were either independent or not independent. But if we have 3, then we have pairwise independence, but also we have this 3-wise independence. So we would have to show all possible combinations of 2 events plus all possible combinations of 3 events. Right, so yeah, to show that they are mutually independent, I have to show they are pairwise independent for all of the events. Plus, I would have to show all combinations of 3, that the intersection of these events is equal to the product of the individual probabilities. Okay, so pairwise independence and mutual independence is, still around for random variables. Okay. So again, there's a lot of symmetry here, so this will go sort of quickly, but not this one, but this one. Okay. So let's see exactly what this is asking. So my random variable X. All right. My random variable X is 1 if X is divisible by 2, right? So X is my uniformly random chosen element from this set. So if X is equal to 2, then big X is equal to 1. If little x is equal to 3, then big X is equal to 0. If little x is equal to 5, big X is equal to 0. If little x is equal to 30, then big X is equal to 1. So, well, let's draw out these. This is 2 and 30. So this is the event X equal to 1. And so we've gone over that. So let's talk about what S really is. So S is 3 prime numbers, 2, 3, and 5. So if it's divisible by, 2 is not divisible by either of these, and neither are 3 and 5. They're only divisible by themselves. And 30 is the product of all 3. So 30 is divisible by 2 and divisible by 3 and divisible by 5. Okay, so there's a lot of symmetry here, even though these appear to be weird numbers. So y is, yeah, and then this is 0 otherwise is 3 and 5. Okay, so x equal to 1, x equal to 0 have equal probability of 1/2. Oh yeah, what? Oh no, sorry, this is x equal to 0. Yeah, I know. I'm just running out of space here. But yeah, you would be correct for that, 3 and 5. Okay, so x equal to 1. Yeah, let's omit that. Just in the interest of space. We know that both of these events are the same size, so they have the same probability. X is divisible by 3, that is 3 and 30. And x is divisible by 5, that is 5 and 30. Okay. All right, so to check if they're pairwise independent, we want to check, yeah, we have a bunch to check, but we will do some of them and then we'll just say the rest are symmetric because they are. So I want the probability that x is equal to 1 and y is equal to 1. And I want to prove or disprove that it's equal to this. Okay, so the intersection, x equal to 1 and y equal to 1, well, that's all the elements they have in common. This is just the outcome 30. The probability that x is equal to 1 is 1/2. Probability that y is equal to 1 is 1/2, right? It's simply 2 over the size of the sample space. This is, if I put, the size of this over the size of the sample space, I get 1/4. So yeah, 1/4 is equal to 1/2 times 1/2. So x equal to 1 and y equal to 1 are independent. Really, we know everything on the right-hand side is going to be equal to 1/4, right? Every single event defined here has probability of 1/2. So the product of any two events is going to have a probability of 1/4. So we just have to look at the left-hand side. Okay, so if all of them are equal, all of them has size 1, then we're done. So let's take a look at some other ones. X equal to 0, y equal to 0. All right, so this, let's actually draw these in now. This is 3 and 5. And this is 2 and 5. So x equal to 0 is 3 and 5, y equal to 0 is 2 and 5. They have 5 in common. So this is, the size of this event over the size of the sample space. It's 1/4. So yeah, this is equal to 1/4, and we'll look at one other example. X equal to 0, and well, let's say z equal to 1. What's in that? Well, x equal to 0 is 3 and 5. Z equal to 1 is 5 and 30. They have 5 in common. So yeah, this is equal to this one outcome over the size of the sample space, which is 1/4. So yeah, and then the rest are all symmetric. Okay, so these 3 random variables are pairwise independent. Okay. All right, so now we want to show that they're mutually independent. So, or not, right? So if we can find values for x, y, and z such that they all can't be true at the same time or all non-empty at the same time, then we're essentially done. Okay, so let's say I want something that is not divisible by 2, a number that is not also not divisible by 3, and is not divisible by 5. Do we have such a number in our set? Right, so 30 is if I look at all the prime factors, it's 2 times 3 times 5. So that's divisible by all 3. 2, 3, and 5, well, they're each divisible by themselves. So if I wanted a number that's not divisible by 2, 3, or 5, that's going to be empty, right? There's no such number in that set F. So the probability x equals 0 and y equals 0 and z equals 0 is 0. Okay, so they are not mutually independent, although they are pairwise independent. So that means if I tell you that, y is equal to 0, so it's a number that's not divisible by 3, and it's a number that's not divisible by 5, then I've narrowed down the values of x, possibly. Yeah, then I know that x must be equal to 1. Okay, questions? Yeah. Yeah. Yeah, probably. Yeah. Yeah, I did move through that kind of quickly. Again, there's a lot of symmetry there, and I didn't want to, we've already done all the painstaking work, but yeah. Yeah. So the probability that this event happens is equal to 0. For them to be independent, that would have to be equal to the x equal to 0 times y equal to 0 times z equal to 0. We know the probabilities of each of these is 1/2 times 1/2 times 1/2. So that's 1/8. So 1/8 is not equal to 0. Yeah, so yeah, you're right. I should do that. I told you guys to do that if I ever ask you to, but yeah.
Like, if we just say that we know all the probabilities at the bottom parts here.
Yeah, you can, again, yeah, just be careful, right? As long as if you've already found these probabilities, then that's great. You say, well, look, I already found them. None of them are 0. Yeah, that's fine. If you haven't found them, then you should find them. All right, other questions? That's not a question. Okay. Okay, so that's enough for independence. So yeah, all right. So let's start on the expected value, which is kind of when we start to use independence in order to prove stuff. Okay, so again, just a review of where we're at in terms of our material. We have a sample space, we have outcomes, we have events, which are just subsets of the sample space, so some collection of outcomes. We have our probability function that each of these outcomes has a value. They all sum up to 1. And then we can have random variables. And if you want to remember what they are, they're neither random nor variable. So that's what we know so far in terms of probability. And so, yeah, if we look at any given, we can define an event based on the value of our random variable. So in this case, this is the event x equal to k. It's just a subset of the sample space. But each of these outcomes has the same value, so that, tells us something. But let's look at a sample space A, B, and C, and a probability function on that sample space. So I'm going to select one of these, at random. A with probability 4/5, and B with probability 1/10, and C with probability 1/10. And I'm going to define a random variable on them. So x, if I pull an A, then x is equal to 1. If I pick B, then x is equal to 2. And if I pick C, then x is equal to 3. Okay. All right. Now, what's the average value of x? So let's define average a little more precisely. So I perform, so this is my experiment. I choose A, B, or C with the given probabilities. And then I record the value X. And I do this 1,000,000 times, and I divide by 1,000,000. Right, so that's the average value. So what's the average here? Or what's it not? I mean, so the first intuition is just our old high school definition of average, right? 1 + 2 + 3 divided by 3. That is the average of the numbers 1, 2, and 3. But when we're performing this experiment, we really expect to pick A a lot of the time, right? In fact, we're going to choose A 80% of the time. So that means the average is going to be skewed by our probability function, right? So it's not going to be this. I'm going to have to account for the fact that A comes up the most, which means that I'm going to record a lot of ones over my 1,000,000 experiments, right? And in fact, about 800,000 ones. All right, so the expected value of a random variable X is the average, but it's the weighted average. It's the average weighted by the probability that you will get that value. Okay, so it's a weighted average. So I'm going to, factor in the proportion. So I get X equal to 1 4/5 of the time. And I get X equal to 2 1/10 of the time. And I get X equal to 3 1/10 of the time, right? So these are simply, this is the probability of the event X equal to 1. This is the probability of the event X equal to 2. And this is the probability of the event X equal to 3. And then I solve this expression and I get 13/10. Right, so if I perform this experiment 1,000,000 times, recorded the value of X, and then took the average, it would be very close to this. Okay, questions? All right, so yes, and of course, if I take the sum of the weights, well, the weights by weight, I mean the probabilities, of course, these have to sum up to 1. In order to get an average, I have to consider every possible outcome, right? Every possible outcome along with its, essentially my random variable and all the events it defined have to, again, span the entire sample space. Okay, so yeah, this is essentially, if I run the experiment 10 times, I would expect to get A 8 times and B and C, I would expect to get once each because of these probabilities. Okay. So our official definition of expected value for a random variable X is I take all of the possible outcomes and the values that it gives my random variable X times the probability of that outcome. Okay, so in our example that we just did, this looks like, well, the value of X given A, which is 1, but drawn out explicitly here. I've selected A. I plug it into my random variable function, multiply times the probability that I get A. Plus B, I plug it into my random variable X times the probability that I get B. And C into my random variable X times the probability that I get C. Okay, so this is our official definition of expected value, and this will give you the average, the weighted average of any experiment and given a random variable X. Okay, questions so far? All right, how are we doing? 15 minutes. Okay, so let's look at an example. In this case, we have a uniform probability, so it's actually going to be a little bit easier. So this is a fair die. It can take on the values 1 through 6. And each of these outcomes has probability 1/6. It's a uniform probability space. And then I define a random variable X, which is simply the result of the roll. So whatever the value of the die, that's the value of my function or random variable x. So xi is mapped to I. So now I take my definition of expected value. It's the sum, right? I look at every single outcome and I take the value that that outcome produces in my random variable times the probability of that outcome. In this case, all of these probabilities are uniform. They're all going to be the same. So yeah, this is equal to 1 times the probability that I get 1, plus 2 times the probability that I get 2, plus 3 times the probability that I get 3, et cetera, et cetera. But all of these probabilities are going to be 1 over 6. So in a uniform probability space, the expected value is simply the average, right? So here I get 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by, well, 1/6, which is really just divided by the size of the sample space, not divided by 1/6, but divided by 6, which is the size of the sample space. Okay, so here it really is the average. So I roll a single die and the expected value is 3.5. Right, so yeah, obviously you can't roll 3.5. So average does not mean, any number you're likely to see necessarily. It's simply the average. Okay, yeah, and this is the, whenever you're having trouble with what this actually means in terms of the real world, well, I performed the experiment a million times under the same condition, and I just list all the outcomes. Okay, questions? All right, so let's take a look at another random variable y. And this random variable y I will define as 1 over the result of my roll, right? So yeah, if I roll let's say if I roll a 1, that's equal to 1 over 1 or 1. If I roll a 2, that's equal to 1 over 2. If I roll a 3, that's equal to 1 over 3. So this is, in some sense, y is equal to 1 over x, right? So x is the result of my roll, and y is the 1 over the result of my roll. Okay, so now if I look at the expected value of y, using my definition of expected value, this is all of the values that y takes on. Each of them has probability 1/6. It's a uniform probability space. So I can, since this 1/6 is not dependent on this variable I, it's a common factor. I can factor it out, take it outside of my summation, and then I get 1/6. 1/6 times the sum of all of the possible values of y. Okay, so 1/6 times 1 over 1 plus 1 over 2 plus 1 over 3, etc. We find a common denominator, and then we can sum them up and finish this little equation. We get 49 over 120. Okay, so that's, again, we can define random variables any way we like. So, but in this case, we did it because y and x are definitely related. So maybe the natural question might be, is the average of y and x related? So the expected value of y is equal to the expected value of 1 over x, and it's 0.4 something. The expected value of x is equal to 7/2 or 3.5. 1 over the expected value of x is 2 over 7, which is 0.286. Right, so in general, even if y is equal to 1 over x, it's not the case that the expected value of 1 over x is equal to 1 over the expected value. Expected value has a lot of neat properties. This just happens to not be one of them. All right, questions? Okay. All right, let's look at another slightly more interesting example. So again, we talked about how we actually were doing, we were using random variables earlier. So this is the table that we saw then. So we have a sample space now where we roll a red die and a blue die. And each of these outcomes is with uniform probability. So each of them has probability 1/36. And we can map that to a random variable x, right? So x is equal to the sum of the two dice, which is, a very, very natural random variable to define. So x is equal to ij. So this table is really a table of our random variable x, right? So x11 is equal to 2, x12 is equal to 3, etc. Okay, so this table is a mapping of our random variable. So we want to compute the expected value of rolling two dice. So what we want really is the average, the weighted average, but in this case, it's a uniform probability space, so they all have equal weight. So we really want the average of all of these numbers, right? So these are all the possible rolls. They all happen with uniform probability. I want to take the average. Okay. There's 3 ways to compute it. Do we have enough time? We have enough time to do, yeah, maybe. All right. We have enough time to do the 2 hard ones, and then hopefully we'll get to the easy one next week. So we're going to go in order of difficulty. So all of these ways to compute expected value are derived from this definition, right? So it's always mapped back to this. So we'll start with that. Okay, so I want to take each outcome and the value that that outcome maps to in my random variable x times the probability of that outcome. Well, we know the probability of that outcome is 1/36. So what I want to do is sum up all of the values, right? So I'm just plugging these into this equation now. So all of these probabilities are the same. They're all equal to 1/36. So I take that out as a common factor, and it's 1/36 times the sum of everything in my table. Okay, so that's the hard way to do it. There's a lot of symmetry here. You could probably do it actually without too much difficulty. But in a brute force sense, I would just add them up, maybe write a program. 252 is the sum of all of these values times 1/36. So I get 252/36, which is equal to 7. Okay, so if I roll 2 dice, 2 fair dice, on average, the outcome of the sum of these 2 dice is 7. Okay. All right, questions? Yeah. Okay. All right, so we want something shorter and easier. I mean, here there's a lot of symmetry we could take advantage of, but we don't want to rely on that. This is the hard way to do it. Let's take a look at, well, we talked about random variables and how we can map those to events based on their value. All right, so if we look at this, for instance, xij maps to the value 4 3 times here. Okay, so this is an event now instead of individual outcomes, and every outcome in this event has the same value. All right. Okay, so I want the event itself, x equal to 4, is equal to these 3 outcomes. These 3 outcomes all map to the same value. And they all have the same probability, but I can determine the probability of this event as a whole. Right, so this has probability 3/36, simply the size of the event over the size of the sample space. and each, this entire event all have the value 4. Right, so if I look at my original equation, well, it's the value times the probability of that value, but I can gather those values into an event, and then I can look at the value times the probability of an event. Okay, so this is, again, I mean, it's not really, we're not doing anything different. We're just looking at it differently, which sometimes helps. Okay. All right, so this is the definition of an event. This is exactly how we compute the probability of an event. So the probability that x is equal to 4 is equal to 3 over the size of the sample space, or 3 over 36. Right. Are we covering a lot of material today? Am I losing you guys now? Am I going fast? I don't know. No, everything's fine. Everybody's good. Awesome. Okay. Okay, so what we're going to do is we're going to rewrite this sum, right? So, in all its brutal, completely written out, but then we're going to gather terms that all have the same value in front of them. So all these terms have the common factor, which is the value of that random variable. Right, so I now look at this expected value x, I expand this out, but I gather all of these outcomes into their events that all, where the outcomes all have the same value, right? So this is all of the outcomes that result in a value of 2, all of the outcomes that result in a value of 3, all of the outcomes that result in a value of 4, and over all possible values that my random variable x can take. And then I just look at the individual probabilities of each of these events, which, I mean, right, so the probability of getting a 2, well, there's only one, it's 1 over 36. 3 is 2 over 36. 4 is 3 over 36. 5 is 4 over 36, et cetera, et cetera. All right, so we're taking a little bit of advantage of the symmetry here. Sometimes this works way, way better than the other way. You can always do this, but sometimes this is easier. Of course, this is not even the easiest one. But yeah, I still get 7. All I'm doing is I'm using this same summation, but I'm just rearranging the order of the outcomes so that all the outcomes with the same value are grouped together into events. Okay. So the former method, we had 36 entries to add up. Using this method, there's 11 entries to add up. Again, we're still doing a lot of math, but hopefully it's a little bit easier. You'd still have to, this would be difficult to compute by hand. So the idea is now we want to look at a third solution where we can actually, we don't even need to compute barely anything, right? We're going to do one addition and we'll be done. So that's called linearity of expectation. And it is far, far easier than anything we've seen, but we're not going to see it this week. We'll look at it next week. The idea behind it is, well, if I have 2 dice, I know the expected value of one of those dice. Well, it just so happens that if I want the expected value of rolling 2 dice, it's just this, I just add up the expected values of each individual one, right? So that's the idea, no big secret, but we're going to prove that next class. Okay, so that's it for today. Yeah, get your assignment 3s in and have a good weekend.